Okay, the screen is visible now?
Yes, sir.
Okay, fine. So last time we were discussing about MESFET, the structure, basic structure of MESFET, and what we are going to do today. Today we are going to compute, find out the expression of IV characteristics. So I can write here like this is IV characteristics. Okay, and if you can. And if you can remember properly, like what was our actually structure? So you know that you have a source, you have a drain, and you have a gate. Here is one thing is very important, that what is the nature of gate, and that we already know, right? So nature of gate, and so like source and drain should be ohmic contact or low resistance contact. Okay. And hello. Some noise is coming. Okay, fine. So source and drain is ohmic contact that we know, and gate is actually called rectifying contact. Why rectifying contact? So if you can refer our last day discussion, you see that somehow we had to close this junction, and if you want to close this junction, you need to have a reverse bias so that the reverse bias can extend, close this this part. So for an example, like suppose I am having like, what is this part? So like what is this part? So this part I'll have a discussion later on, like whether people are saying it's a semi-insulating materials. Okay, what is semi-insulating materials and why we need it? So that we'll have a discussion later on, not now. Okay, so and here you can see, due to some reason we are using N-type semiconductor. Okay, I'm not telling you the N-type semiconductor, like whether it is a N-type silicon or N-type gallium arsenide or N-type gallium nitride, that call will take at the end of IV characteristic formulation, but not now. Okay, so you just assume that it's a N-type semiconductor. Okay, that's the thing. And if you can remember our last day discussion that we had, like if you want to close this junction, you need to apply some gate voltage, right? If you can remember our, so if you want to, so like your gate voltage VGS should be reverse bias, because only then only you can have reverse bias, so that you can close this junction, right? And if you want to close it, so it will looks like this one only, right? You can understand. So in that case, what we are telling that I D is that drain current is 0, and at the voltage at which this closing is happening is VP0, pinch of voltage. Okay. No, here in this definition, no, I'll let us modify it to the voltage, gate voltage. At which the channel is closed. We are telling it is closed. So we are writing VP0. So here actually I have to clarify nicely. So no, you know that just recall our discussion in Schottky junction diode. You know, if you apply to get to source voltage, right? So can you remember that what is happening? Suppose it's a reverse bias. Just for an example, like if you have a reverse bias, and this is my equilibrium state, right? Correct, right? So you have a 5N and you have a VVI, right? Now, if you want to make it reverse bias, what will happen? You know that part very well. So, but just for an like, right? And what is this voltage? VVI minus, so VGS. So look at this part. Look at this. So we normally write this built-in potential, even if we apply reverse bias as VBI minus VGS. For an example, like if it is a reverse bias, you know, what is reverse bias? So you are actually applying negative voltage over there, no? So VBI minus VGS, right? So it is actually VBI plus VGS. Similarly, if it is a forward bias, you understand what it is actually VBI minus plus VGS. Because you are applying positive voltage, so VBI minus VGS. Right? So what is my general formula? General formula of this relative built-in potential, the voltage across this depletion region. So you can write general built-in potential under any bias. You would normally write VBI minus VGS. That's what. Like if VGS is negative, that's what you are getting reverse bias. So you will get a VBI minus plus. So that's what you are getting reverse bias part, VBI plus VGS. And if it is a forward bias, that means you have to apply positive voltage across your gate. So it is VBI minus VGS, right? So general, actually we are writing actually this. So if someone is asking like what is the, so this is true for here also, like what is the potential drop? So for an example, like it should not be like that. I'm just drawing it nicely. So for an example, like what is the voltage drop? So like, what is the potential drop across, right? See, you can write VBI minus, sorry. Yeah. You can write VBI minus VGS, right? Now, thing is that VBI minus VGS, right? Now, if your VGS is such that, so that's what I'm writing. If VGS is such that the gate voltage at which the channel is closed off, and that is called the VP0, right? So if you look at this definition, that your gate to source voltage is that gate voltage at which the channel is completely closed, right? So it means like you have a VBI. Now you have applied some gate voltage, okay? And if this condition, you getting a voltage where channel is closed, So this voltage we are calling pinch off voltage, and this gate voltage is called the threshold voltage. So that is very important. Try to understand, like you are applying a voltage over here, gate to source voltage. VBI is already there. VBI, like if when you have not applied any gate voltage, so what is your built-in potential? VBI only. Okay. Now over and above, when you apply some voltage, in the general formula, we are writing VBI minus VGS. Okay. Now your GS is such that VGS is such that it closes the junction at that voltage of gate to source. It's called the threshold voltage, and total part we are taking about VP0. That's what I'm writing. Right? So please remember this part carefully. And you see, what was the discussion last time? When you try to close your junction and when you try to switch off the current, total current by gate, okay, it is highly possible that like you have some current flowing and now you want to close this junction or close the channel so that you have a current which is zero, and that is possible by gate. Now there is another condition where you want to close this junction, or sorry, you want to close this channel by drain to source voltage, also possible. But in that case, we know your channel may be pinch off, but you will get always a current, which I'll have a discussion. Remember, again, if you want to close this junction by gate to source voltage, it is possible. In that case, your current is zero. But if you want to close this junction by drain to source voltage, you are trying to close this junction tentatively, approximately, but your current never be zero. So this part I'll clarify it a little bit later. What I try to mean, but try to understand this situation nicely. VBI minus V threshold volt is equal to VP0. Okay. Now what here another thing. So if we try to point it out, so this is my A. A is the total thickness of this N-type gallium arsenide. Okay. So what is my pinch off voltage? Pinch off voltage, we know the formula, right? So just think about our formula for A under root. Can you please tell me? V. Please tell me what is the value. So this is the voltage. So you know that formula, no? For PN junction diode. If you see the PN junction diode formula, so we always write these things, no? QND and epsilon into VBI, right? So there is some sort of 2 factor is there somewhere, so you please check it. But this is a formula that we always write, no? Now here in this case, you have to XD, you have to write A, because now your depletion region is such that you have to close it. So your XD has to close full, right? Now this XD is nothing but the whole thickness, so that's why I'm writing A. XD is equal to A, right? And you can write XD is equal to A. So you can get it from PN junction diode formula, from junction diode study. We have done it, right? So we are writing A, and A square means 2 epsilon VBI into QND. Okay, so here what is the potential? Instead of VBI, you have to write. So VBI, you have to replace it by pinch off voltage, right? So you have to write pinch off voltage, QND square. Yeah. So this is the formula for that pinch off voltage, right? we have got it. And definitely, if you are still are very particular, you can write it is actually VBI minus V threshold also, UND. Okay, so this is the kind of formula that we often, sorry, VP0, so 2 epsilon, 2 epsilon. There is some problem, yeah. So this is the formula that we often use, right? Okay. So that formula, I name it as a 1. Now there is another thing that conceptually we have to understand, right? Now this is all about that you want to close this junction. So it is all about like your drain to source voltage very low as compared to VPI minus V threshold voltage. Then only it is possible, I mean, this formula, right? Right. Now there is another condition where VDS is little bit better, means like little bit high. And in that case, so you can write is a case 2. And how it looks like, you see, you have a source, you have a drain, you have a gate, and what is happening over here? You have a N-type gallium arsenide, N-type semiconductor, right? And it is Si semiconductor. So what you are trying, like you have applied some gate voltage. For an example, suppose you have applied some VGS. Okay. And you have also applied some drain to source voltage, and you are varying drain to source voltage, right? You are varying drain to source voltage, right? So again, we just you can write something like that. So you please find out, because remember, if you want to have a reverse bias, so you can understand this is my positive side, this is my negative side. So plus to minus is my direction, and if you want to make it reverse bias further, so you have to apply more reverse bias, right? So this part you have to be very careful, right? So you have to apply negative voltage across the metal side. So that's what I am doing. I hope it is clear. So somehow what I'm trying to tell you that this here, this VGS, you have to apply reverse bias. Okay. The biasing condition you please check and take a comment. And drain to source, you definitely would understand you have to apply some positive voltage also, as well as so that you can. Now if this portion also you will have like kind of what is called okay, let us see. So let us see that you have, this is actually nothing but VBI minus VGS. You write, I try to write VBI VGS. correct? And now this portion, what would be the biasing condition over here? This is a little bit confusing, so let me draw it. Like, okay, so you are applying drain to source voltage. So definitely, with respect to drain source, it is actually positive. That's what I'm saying. Now, when there is a VDS is 0, drain to source voltage 0, and you have already applied gate to source voltage. So what is the voltage drop you are getting across your channel? So across your channel, you are getting the voltage drop is actually VBI minus VGS, right? Now what you are doing, even now you are actually slowly increasing your voltage, right? Slowly, you are increasing drain to source voltage. So what will happen? The moment you slowly increase drain to source voltage, you see this portion. So this portion, I should draw it by red color. You see this portion is nothing but reverse bias. So your condition, so look at this part very carefully. What I'm telling you, after that you put your symbol. Okay, that's what I erased the symbol. One thing you please remember, I have to apply gate voltage such a way that I can extend my reverse bias condition, right? So that I can extend my like what is called, so that I can extend my depletion layer. That is fantastic. Plus, the drain to source side also, you have to apply a voltage, okay, so that you'll have kind of, so you are applying drain to source voltage. Suppose it's a positive voltage if you are applying, you see this portion, you'll have a kind of reverse bias. So this portion you'll have a reverse bias, right? So that means drain side, it is actually reverse bias, right? So the condition you please try to understand. So if this is reverse bias, so you will understand like you have extension of this part, right? So this you please try to check. I'll refresh. I'll read out once more. So the moment when you are in the source sides, when you are in source sides, the voltage VBI minus VGS. Okay. The moment you go towards drain side, you see the channel is the depletion layer is try to increase. Why? Because you have also applied reverse bias condition across this drain side also. This is very important because this condition, the moment you apply some positive voltage over there, so what will happen? You'll see that this there would be kind of such a kind of extension of your depletion region. Now, if you go back in the source side, so if it is a source side and if it is a drain side, so you'll see what is the voltage at source side. Voltage across the source side is VBI minus VGS. And what is the voltage across your drain side? VBI minus VGS plus VDS, right? Because, right. So that means if you try to just try to draw it separately, you'll see in this manner. Right? And So this is source side, this is drain side, okay, and across the drain side and across the drain side, I can write what is the voltage. So here the voltage drop is actually VBI minus VGS plus VDS and across the source side it is VBI VBS, okay, because you know whatever voltage you are applying into drain sides, it won't have any effect on source side. Why? Because source side is grounded. So that is the one of the reason the source side is grounded. So now please try to understand this bias condition. What I am trying to tell you that this source is grounded. Now get to source voltage such that you will get extension of your depletion region. So maybe it is reverse bias. So I am writing R. Similarly, drain to source voltage is also reverse bias, right? So why it is reverse bias? Then only you will get a current flow across this from source to drain, right? So that is the one of the condition. So now the question is coming, how do I understand like whether my drain to source voltage is positive or negative? Don't do that part. So what you have to do, you write plus VDS. It is a kind of general formula. If you apply drain to source voltage positive, then it is a positive. If you are applying drain to source voltage negative, so then it would be negative. Okay. So here also it is kind of general formula, but what is important, don't look at the polarity. It is actually general formula. Okay, so you have to write in this way, don't look at the polarity, rather than you look at what you need. What you need. Now here actually what I'm trying to understand, like trying to tell you, so suppose there is one condition, like you have both the source side and both the drain side, it's like that only, right? So like you can understand this part, like, so in that case, here in this case, my VDS is equal to 0. Okay, so the voltage drop of any portion, voltage drop at any portion between source and drain, it is VBI minus VGS, because source side is also 0. No, you have applied source is equal to 0. That is actually by default, and I am telling you that your drain voltage is also 0, right? So that means voltage is the voltage across your channel length L, the voltage across your channel is actually VBI minus VGS, any portion. But what's about the voltage across between source and drain? If you are applying drain to source voltage not equal to 0, it is actually function of, and if it is a x-axis or if it is a y-axis, right? So the function, so if it is a y-axis, so okay, so at the y-axis, so you see one end you are getting VBI minus VGS, another end you are getting VBI minus VGS plus VDS. So how to write a general equation? So you can write general equation VBI minus VGS plus VY. Okay, so you write, so how you are writing? The voltage drop across channel, voltage drop across channel, you see, if it is length L, so suppose this coordinate is 0 and this coordinate is L, so you can write voltage drop across the channel, length is equal to 0. It is VBI minus VGS. And at L is equal to L, sorry, Y is equal to, sorry. Y is equal to 0, it is this one, and Y is equal to L, it is VBI minus VGS plus VDS. So this is the voltage drop actually we are actually applying throughout the channel. Now the second question is asking, right. So let me represent this part from this part. It H is the height. So you know from here to here it is actually A, and this H, let me write H is equal to X, right? So you write like that. And what is my open? Because remember, whatever the channel is left, that is the portion your current is flowing. Whatever the channel is left, that through this left portion your channel is flowing. So means, what is the left portion I can write? I can write A minus HX. So that is the portion my current is flowing, right? That you actually understood, right? So because your current is flowing, suppose VBI minus VGS, just remember our last day discussion that your current is flowing through the left portion. Okay. So if you apply some voltage, so your current is flowing through this left portion. Similarly, in this case, because if you want to have a current flow, definitely you have to apply drain to source voltage. And if you are trying to apply drain to source voltage, you will see the depletion layer behavior looks like this one only, right? And it is a function of X, right? So X at 0 and X at equal to L. So it is a different value. So it is a function of X. So that you please try to remember that. So what is the leftover portion? A minus HX, and through A minus HX my current is flowing. So that we have to calculate. Before the calculations, now the question sometimes asked by a lot of people like, okay, it means that if it means the following things, how to explain this part. For an example, like you have this kind of things, right? You have a source side, you have a drain side. That means X is equal to 0, this portion, and X is equal to L, this portion, right? You have applied VPI minus, so suppose when VPI minus VGS is equal to 0, let me write, when VPI minus VGS is equal to 0, you have this part. The voltage inversion charge is throughout the same, right? When you increase, so this is my V, when you increase that drain to source voltage, what will happen? You'll get some extension over here. If you try to increase the farther, you'll get farther extension. If you try to increase farther, you'll get a farther extension. You understand, right? So that means it's this drain to source voltage. What if you try to increase it, your depletion layer across the drain side is try to increase. Just like here, your depletion layer across the drain side is try to increase. The question is the following. It means, can I close the junction? Can I close this channel by increasing drain to source voltage? Can I do it? I mean, like, so that is actually great question that needs to be answered, because here I told you already that you can close this junction. You can close this junction with get to source voltage. And I already gave an answer, like you cannot close this junction by drain to source voltage. Why? Why means the explanation, I don't know whether there is a good explanation is available in the market. Frankly speaking, I don't know, because I was trying to search a good explanation for this part, this behavior of pinch up condition, trying, but frankly speaking, I have not got it. Okay. So that's what I was trying to understand when I'm trying to give you a kind of model which you can adopt or you can modify on it. Okay. Again, I'm telling you, there is no standard method or standard theories available to tell you the fact what I explained. Even whatever book, even if you go to JFET, you can see that you can extend that PN junction things up to some level, but beyond that, you cannot extend. So this theory, why you cannot go beyond that, or why you cannot completely close the junction or completely close the channel by drain to source voltage, really we don't have a good justification on it. But let me try to convince, like, whatever way that I am trying to tell you, it might be taken up. Like, that's up to you. The thing is that look at the drain side. So why this drain side has appeared? The drain side has appeared due to, because you have applied your drain to source voltage. The first thing that why drain side looks like that, because you have applied drain to source voltage, right? That is why it is actually bended fast, bended largely. And that is why there is a dome-like structure. Now the question is, so these things you can explain a series of resistance. So resistance amplitude is increasing. The source side, there is no problem because you have enough channel thickness. So my resistance is low, but whenever you go towards the drain side, what you can understand, my resistance is high. And that's what I have given a large amount of resistance, right? Now your current is flowing through that. Your current is flowing through that. So your current is flowing. So this voltage drop, you can understand the voltage drop V1, voltage 2, V2, and it is V3. So V1 is nothing but your current through and this resistance. The resistance what I have shown you. Similarly, V2, current is constant, no? I into R2. V3, I into, so you can write it in this manner like V1 is equal to I into R1, V2 into I into R2, and V3 is equal to I into R3. And another thing is that your R3 is higher than R2 and higher than R1. Okay, now, so is this process called the P-spite modulation you can think about. Now what happened? You are getting current, fine, no issue. Now suddenly, suppose a situation T1, so suppose a situation T0 you have arrived, and that T0 arrived, you have closed this junction. Suppose you have applied drain to source voltage at such a level, you close this junction. Then what will happen? If you close this junction over there, you understand the current is 0. But current cannot be 0. Why? Because because this current, you cannot make here current is 0 because current is flowing. Okay. If you want to make current 0, that means your drain to source voltage has to be 0. Remember that. What is that? So V3 you can represent it actually VDS. I into R3. Right? So because it is last time. So if you want to current, because the moment you close it, your current is 0. If the current is 0, your VDS is equal to 0. Right? But you cannot make VDS is equal to 0. Why? Because you have applied drain to source. You have already applied your VDS. Right? For an example, like if you want, just for this case, let's try to understand. So at t is equal to 0, you make I is equal to 0, and which VDS is equal to 0. In this condition, what will happen? VDS is equal to 0. You can write VBI minus VGS plus VY at drain end. At drain, you need to write VBI minus VGS, right? Because at drain end, VY is actually nothing but VDS. So when you put VDS is equal to 0, so you can write VBI minus VGS plus, okay, so you can write in this manner, just for understanding purpose. So at drain end, you can write VBI minus VGS plus VDS at drain end, right? So in this case, what will happen? But you have put VDS is equal to 0, so you'll get VBI minus VGS. So what will get? What will happen? Look at that. You have closed this junction. You have closed this junction. The moment you stop flowing the current, your VDS is equal to 0. The moment VDS is equal to 0, what is the overall potential? VBI minus VGS. Again, it will open up. Because why VBI minus VGS? Look at that. VBI minus this the voltage drop, where this is my voltage drop where we have opening. This is my VBI minus VGS, and this is this condition. This is my VBI minus VGS, which has opening, right? Now, the moment you say that I have closed my junction, the moment I say that I have closed my junction, that my drain to source is equal to 0. At the moment drain to source is equal to 0, so what is the voltage across your channel? That is actually VBI minus VGS. And you know the VBI minus VGS condition. VBI minus VGS voltage means you have opened up your junction across this level, right? So what it means, like you try to close it, but it will try to open it. You are trying to close this junction by drain to source voltage, but the moment you are trying to close this junction by drain to source voltage, the moment you try to close this by drain to source voltage, immediately the voltage drop will appear as a VBI minus VGS. So it will immediately open it. Again, you try to close it, it will immediately open it. It will try to close it, it will immediately open. So that means it will become an equilibrium condition. Neither open, neither closed. Okay. So that is why there is a small opening, very, very small opening. So this condition. So what I am trying to tell you that this is the very small opening is still left over there. And that cannot be closed always, because the moment you try to close it, it will make VDS is equal to 0, but you have applied VDS, so you cannot make it 0. And even if you turn VDS is equal to 0, your voltage becomes, the total channel voltage becomes VBI minus VGS instead of VBI minus VGS plus VDS, right? So what I'm trying to tell you that your voltage is like VBI minus VGS plus VDS. Okay. Now, it is actually closed condition. You have closed condition, but this enable VDS is equal to 0. So you'll get the voltage across the channel is equal to VBI minus VGS, which is nothing, open condition. So there is a closing and opening, closing and conditions are achieving. At equilibrium, we say that it is kind of negotiation, neither close nor open. So very little. So what we are trying to, what we are telling, like this is my conditions. You have like this condition. So this is my source side, this is my drain side, this is my 0, this is my L, okay, and this condition, and you see this is my A. So here we approximation is that you almost closed. Approximation is the almost closed. Little opening is there, but we just approximation is that almost close this junction, almost. And the voltage, the drain voltage at which the height Hx very close to A, we are calling pinch off. Because just why, okay, try to understand. So we have already defined the voltage, the condition at which my channel is closed, the condition at which my channel is closed. So I'm calling it is a pinch off voltage. Now, when we can have a pinch off voltage, so VBI minus VGS, and we are writing VD SAT, saturation voltage. Because why it is called the VD SAT? Because like suppose at particular voltage, at particular drain voltage, you are getting VD SAT. At particular drain voltage, we are saying it is a VD SAT, and at that VD SAT, you are almost close this junction, right? So that is why I am writing the drain voltage at that condition at which my channel is almost closed. So I am writing it is as a VD SAT. Now you may ask, what will happen if I still increase my drain to source voltage above VD SAT? What will happen? In that case, your junction will looks. In that case, your junction will increase in the other side. For an example, like, so suppose, just for an example, like you have this kind of situation. And this is the voltage at which you have received these things. So I am talking about VD SAT. If you still apply more voltage on it, so what will happen? Your junction will increase this side or this side. So there won't be any increase on vertical side. There would be increase of horizontal side. Because anyhow, you have applied more drain to source voltage, charge balance has to be there. To get a charge balance, you need to open up more negative charge. And how to open up more negative charge? Either you have to open your depletion region in the horizontal section, and that is why it is. So if you apply more voltage over VD SAT, it will go left or right, because you understand that you cannot close this junction. Then what is the option you left? Either you go that horizontal, not this direction, you have to go other directions. Okay, so that is why. So that is why I'm writing it is VD SAT. And since it is almost closed, my junction. So this condition I'm writing VP0. So you will remember the condition very carefully. Like we have already achieved another condition. So this is one condition. And when you are applying drain to source volt, another condition you already achieved. This is also VP0, right? This is also one. But here actually VD SAT is equal to 0. And here actually both VGS and VD SAT, VD SAT not equal to 0. VDS not equal to 0. So these two conditions you please try to understand. So I'm going to share you this video lecture today itself. What my request is that you go back and try to understand this phenomena once or repeatedly, okay, and try to create your own world to understand it. Try to convince yourself. So this can be a reason to understand this phenomena, okay. Still, I have not touched the IV characteristics. I don't think I can touch today. Tomorrow morning we'll start 11 o'clock, but try to convince the pinch of condition carefully. So at gate voltage, you can close it, but at drain to source voltage, you cannot close it, because gate voltage is trying to close it like that, and drain voltage try to pull it out, right? So it will push this side. Drain voltage try to close it. Gate voltage, you try to close this junction, but the moment you apply drain voltage try to pull this condition. So the overall things will pull it on this side. So try to understand, try to convince yourself. That's very important. Okay. So I'm stopping over here. Please. Tomorrow I have another meeting. So why not you have a discussion tomorrow 11 o'clock. And if you have any problem to understand these things, we'll listen from you. I'll listen from you. Okay. I'm stopping over here.